Today we're representing real numbers on a number line, and then we're rounding and finding absolute value also. These are all related topics because it all represents how numbers work on number lines. A number line is a line in which numbers are marked on increments used to illustrate simple numerical operations. An increment is the equal spacing between each tick mark on a number line. Notice I said equal spacing, and each number when you're marking on a number line needs to be on its own tick mark. So plot each group of numbers on the same number line. So we have -5, -1, 2, and 3. We can't just write -5, -1, 2, and 3, because the space between here to here is 4, the space between here and here is 3, and the space between here and here is 1. That means our increments are not the same, so we can't do that. Instead, we need to find our increments first. These are all integers, so we're going to make our increments worth 1. So we'll start at 0 and then go 1, 2, 3, 4. It's a good practice to go one place further than your highest number and one place further than your lowest number if you can. Then we go -1, -2, -3, -4, -5, and -6. So we can write, we don't want to make it too crowded, so that'll be -2, this will be 2, and then you can see then this is 4, this is -4, and -6. And now we want to mark out where our numbers are on our number line. So we have -5 is right here, -1 is right here, 2 is right here, and 3 is right here. We count 1, 2, 3, -1, -2, -3, -4, -5. It gets a little bit more complicated when we have decimals. So this starts at 3.05 and we end, and our largest number is 3.2. So here we're going to start our increment, our number line at 3.00. And we're ending at 3.2. Let's end at 3.2 just because otherwise we would have to go quite a bit further. So we'll have 3.00 and 3.20. This is the same as 3.2, we just can add another 0 to make it easier for us to count. In between, if we ignore the 3's now, in between 0 and 20 is 10, so we have 3.10. Now we need to split up in between each of these. We're going to have to divide into tens because this is in hundredths, so we're going to divide. This would actually be 3.05 because if we ignore the 3's it goes 0, 5, 10. This one would be 15 and then 20. So 3.00, 3.05, 3.10, 3.15, and 3.20. Notice how I kind of started splitting things in half first? That's because it's a lot easier for your eyes to see half than it is to divide into tens, and you're going to get much better equal increments when you divide into half first. Now we have this 3.14, so we do need to divide every single bar into fifths. 1, 2, 3, 4. So then this would be 3.01, 3.02, 3.03, 3.04, and 3.05. So we're going to keep going. 2, 3, 4. Notice to get 5 spaces, I need 4 tick marks. 1, 2, 3, 4. 1, 2, 3, 4. Now we can start putting our numbers on our number line. So we have 3.1, which is the same as 3.10. So this is 3.1. 3.14, so 3.10, 3.11, 3.12, 3.13, and 3.14 is right here. So that's 3.14. 3.2 is the same as 3.20, so we have 3.2 here, and 3.05 is already marked on our line, but we'll mark it again. Notice when I marked what problems I was plotting, I used the same values we had up here. To mark two odd numbers, all we have are 2 numbers here. We don't have any more numbers, so we can actually just mark 54 and 421. Previously, this one, our increment was equal to 1. This one, our increment was equal to 0.01. This one, our increment is going to be 421 minus 54. So that's 367. So here our increment is 367. So our next number, if we wanted to make another tick mark, would be 788. If we wanted to make another tick mark this way, our next number would be negative 323. So if you're only plotting 2 numbers, all you need to do is write those 2 numbers, because that can be what our increment is. Increments can be any amount you want it to be, as long as every tick mark you have has the same increment. So our numbers plotted are 54 and 421. Our increment was 367, so we can plot negative 323, positive 54, positive 421, and positive 788. Now we want to plot some fractions on a number line. We do have 2 negative numbers here and 2 positive numbers here, so we need to have 0. And then our denominators are 4 and 8. 8 is a multiple of 4, so we can divide our number line into eighths, just like our equivalent fractions. 1/4 is the same as 2/8 when we multiply the denominator by 2 and the numerator by 2. So we're going to divide things into eighths. So our largest number is 3/8 and our smallest number is negative 5/8. So the numbers range from negative 1 to 1. Now we're going to start dividing. We divide this one in 2 and we get halves. If we divide again, we get fourths. Same thing here. There's 4 spaces between -1 and 0. 1, 2, 3, 4. At this point, because we have fourths, we can actually plot our denominators with 4 first. Here's 1/4. So there's 1/4. And then we have -1/4. So we can plot -1/4. And now we still need to divide into eighths. So let's divide into eighths. That's just dividing the fourths in half again. And then we can count 3/8. We count 1, 2, 3. And this is 3/8. For -5/8, we go to the left. 1, 2, 3, 4, 5. And that's -5/8. So for negative numbers, we go to the left. Positive numbers, we go to the right. And once we have the right number of divisions, we can just count 1, 2, 3, 4, 5. When we round, it's a way to approximate numbers to make it easier to perform operations. Sometimes you round to the same place value for multiple numbers. Sometimes you only want to round to one non-zero digit. It depends on what operation you're performing. So this one says we want to round 4,638 to the hundreds. 4,638 to the hundreds place. So if we look at a number line, we have 4,600 and we have 4,700. In the middle is 4,650 and 4,638 is somewhere in here. That means it's closer to 4,600 than it is to 4,700. So when we round 4,638, we're going to use squiggly equals because it's approximately equal to. We're rounding to the hundreds, so it's closer to 4,600. On the other hand, let's erase. When we round, so this one moves approximately equal to 4,600. Now we want to round to one non-zero digit, so 4,638. Our last non-zero digit is the 4. So we want to look at, is it closer to 4,000? Or 5,000, because now 4,000 has one non-zero digit and 5,000 has one non-zero digit. 4,638 is closer to 5,000 than it is to 4,000 on a number line. So when we round to one non-zero digit, this one is approximately equal to 5,000. So it really does depend on what we're rounding to. If we want to round 33,578 to the thousands, we want to look and see if it's closer to 33,000 or 34,000. So 33,500 is right in the middle, but this is a little bit more than the middle, so it's closer to 34,000. So it rounds to approximately 34,000. If we want to look at to one non-zero digit, we have to look at the largest digit we have. So that's the 30,000. So now we're looking to see if it's closer to 30,000 or 40,000. 33,000 is closer to 30,000 than it is to 40,000. So this rounds to approximately 30,000. When there's a 5, so we want to round 55 to one non-zero digit. So we're looking at 50 or 60. But 55 is directly in the middle of 50 and 60. When it's directly in the middle, you always round up. So 55 is approximately equal to 60. When we want to round 0.0543 to one non-zero digit, our one non-zero digit, our largest non-zero digit is 0.05. So we look and see, is it closer to 0.05 or 0.06? This is 0.054, so that means we're closer to 0.05. So when we round, that's approximately equal to 0.05. Notice after we round, we don't put any more zeros after there. That has a lot to do with how we work in science, because that talks about how precise our measurements are. So once we round, no more zeros after a decimal point. If we want to round 0.0543 to the thousandth, that's our third. The thousandth spot is this spot. So now we want to look to see if it's 0.054 or 0.055. The 3 is closer to 43 is closer to 40 than it is to 50. So that's what it rounds to, is the 0.054. The opposite of a number, we do need a formal definition of this, and we do talk about the opposite of a number quite a bit. It just flips the sign to the other side of the number line. The number flips over to the other side of the number line. In general, we change the sign of the number. So the opposite of 45 is negative 45. The opposite of 36 is positive 36. It flips from this side of the number line, so we have 0 and 45 over here. It flips us over here to negative 45. Or, for instance, this one, we have 0 and negative 36. The opposite flips us to this side and makes it positive 36. To write finding the opposite mathematically, we write a negative in front of the entire number. So that means we're writing negative of 45. So that's negative 45. That's what we just found out. Negative of negative 36 is positive 36. And when we talk about negatives, if they're in front of parentheses like this, we're going to say negative of 45. Negative of negative 36. Absolute value is the distance from 0. Distance is never negative. So whenever we have an absolute value, the result is always going to be positive. absolute value is written with 2 vertical bars surrounding the expression. So for instance, this says the absolute value of 4. So if we look on a number line, and we have 0 here and 4 here, the distance from 0 to 4 is 4. So the absolute value of 4 is 4. This one, we have 0 and -4. The distance from -4 to 0 is also 4 units. So the absolute value of -4 is 4. This expression is saying the opposite of the absolute value of 4. The opposite of what we found for the absolute value of 4. So the opposite of 4 is -4. The absolute value of 4 we just found was 4, so the opposite of 4 is -4. This is saying the opposite of the absolute value of -4. We found that the absolute value of -4 was 4, and the opposite of that is -4. When we compare numbers, we can think about how they're positioned on a number line. With fractions, sometimes it's easier to make a common denominator. Sometimes it's easier to make a common numerator. So first, we're going to talk about 5.67, 5.672, and 5.793. If we think about how those are positioned on a number line, we can say that we have 5.670, and we can add a 0 because we're not rounding, and because these will all have 3 places after the decimal point. Then we can see that 670 is actually smaller than 672. So then our 5.672 would be next. And then finally, our 5.793. Our directions say to list them from greatest to least, so we're going to say 5.793, 5.672, and then 5.67. Again, I'm writing them how they were written in the original problem, not how I modified to figure out what to do. We're going to erase this, and then we're going to talk about this one. This one, the numerators are all the same because remember 4 is the same as 4 over 1, but the denominators are all different on this one. So let's start thinking about how this is. So if we draw our fractions, the first one is 4 whole amounts. So that's 4. If we divide, let's try dividing into 3. So we have the same size wholes, and then we're dividing into 3. And we're shading 4 of them. Notice that's smaller than this one. The next, we have 4/7. So we're going to divide, we're going to take another whole, about the same size, and we're dividing it into 7. We'll check the 8 and see if we can't see what's going on. So here's 4/8. Notice, as we keep going, these pieces are all getting smaller as the denominator gets bigger. And therefore, if we're shading the same number of pieces and the pieces are smaller, as the denominator gets bigger, the values get smaller. So to list this from least to greatest, we have 4, and then 4/3 is the next one, then 4/7, because the pieces of sevenths are smaller than the pieces of thirds. And then we have 4/8, 4/11, and 4/13. This is different than this one. This is the same size piece. They're all divided into 4, but now we have a different number of pieces. So here we have the largest would be 13/4 because we have 13 of something divided into 4, and then 11/4, and then 8/4, and then 7/4, and then 3/4, and then 1/4. So this is, number of pieces is the same, number of shaded pieces is the same. The size is different. So when the size is different, we think about the size of the pieces. This is the size is the same, and this is the different number of pieces, different number of shaded pieces. So then we look at how many pieces are there that are shaded. So the size is different, this number is different, and that's how you're going to differentiate if you need to look at the numerators or the denominators.